All right, let's get right into it. Today, we're exploring one of the most fascinating ideas in all of artificial intelligence, generative adversarial networks, or as you probably know them, GANs. These are the models behind those super realistic photos of people who don't actually exist, and that's really just the beginning. So here's what we've got on tap. We're going to start with the big idea, the core concept. Then we'll peek under the hood at a specific kind called a DCGAN. After that, we'll cover some essential rules for building them, see all the amazing creative things they can do, and finally, we'll figure out where they fit in the bigger AI universe. Okay, so first things first. The absolute best way to wrap your head around a GAN is to imagine it's a game, a really intense competitive game between two neural networks. They're locked in this constant battle, and that's where the magic happens. So, our two players are the generator and the discriminator. You can think of the generator as the super talented art forger. Its whole goal in life is to create fake paintings that are so good they look like the real deal. And the discriminator? Well, that's our detective, a world-class art expert whose only job is to spot the forgeries. And this is the critical part. Their goals are in direct opposition. The generator wins when it fools the discriminator. The discriminator wins when it successfully catches the generator's fakes. So what happens? They push each other. This constant back and forth, this adversarial game forces them both to get smarter and more sophisticated over millions and millions of rounds. All right, now that we get the game, let's pop the hood and see how one of the most successful types of GANs is actually put together. We're going to look at Deep Convolutional GANs, or DCGANs for short, which are absolute pros when it comes to creating images. So think of the generator like a sculptor starting with just a random block of clay. As you can see here, it starts with a simple vector of random numbers. We'll just call this noise. From there, it uses these special layers to reshape and refine it, progressively making the image bigger and adding more and more detail until, bam, it outputs a complete, totally new image. And this diagram here shows that whole process perfectly. I know it looks a little complex, but stick with me. On the left, you've got the generator taking that simple vector of noise, that little z, and passing it through its layers, which basically blow it up and shape it into an image. Then, that brand new image gets sent over to the discriminator on the right, which does the opposite. It breaks the image down to make a final call. Is this real or is it fake? Now, I gotta tell you, getting this game to work right is notoriously tricky. It's a really delicate balancing act. If the detective, the discriminator, gets too good too fast, the forger just gives up. But if the forger finds one little trick to fool the detective every time, it stops learning anything new. So to keep the training stable, researchers have come up with some key guidelines. Now, these rules aren't just random suggestions. Each one is there to solve a real problem. For instance, using something called batch normalization helps keep the flow of information nice and steady. But one of my favorite rules is the last one, using ReLU in the discriminator. You see, a standard activation function can sometimes just die. It'll stop learning completely. But ReLU makes sure there's always a tiny little gradient, a small spark of learning. It keeps the detective in the game, which means the forger always gets useful feedback to improve. Okay, so we've got the rules in place, the game is fair, and both players are learning. What happens when they get really, really good at their jobs? Well, that's when things get amazing. We get to use these things as unbelievably powerful creative tools. This is where the real magic is. See, the network hasn't just learned to copy bedrooms. It's learned the very idea of a bedroom. It's created what we call a latent space. You can think of it as a giant conceptual map of bedroomness. Every single point on this map is a unique bedroom. And what's so cool is that we can pick 2 points on the map and tell the GAN to just walk in a straight line between them. And what we get is this incredible, smooth as silk transition between two totally different, but always plausible, bedroom designs. Here's another one. In this case, the GAN is acting like a translator. The input on the left is just a basic map. Purple is a car, blue is the road. The GAN takes that simple layout and translates it into a stunningly realistic scene, filling in all the details, the lighting, the reflections, the textures, everything. And it's not just splashing on random color here. That's the key. The GAN has learned context. It knows that leaves are supposed to be green, that butterflies can be yellow. It's digging into everything it learned during training to make smart, educated guesses about how to bring this old photo back to life. This one has some serious commercial potential. I mean, imagine you're a designer. You could draw a simple sketch of a handbag, and seconds later, have a photorealistic product shot. The GAN fills in the texture of the leather, the way the light hits the buckle, everything you need to make it look completely real. Now just look at this transformation. The model isn't just slapping a dark filter on the image. No way! It's completely relighting the entire scene. It's turning on the headlights, changing the color of the sky, adding that glow you'd see from streetlights. It's a total, fundamental reimagining of the photo. Okay, so for our final section, let's zoom out a little bit. Because as incredible as GANs are, they're not the only game in town. They're part of a much bigger family of what we call deep generative models, and it's helpful to see where they fit in. This table gives us a really nice, quick comparison. You have other models like VAEs, which are pretty fast, but their images can sometimes look a little blurry. Then you have AR models, which produce really high-quality images, but they are incredibly slow because they literally generate 1 pixel at a time. But then you look over at the GANs column, and that's their superpower. They hit that perfect sweet spot. They're fast, and the quality of the images they produce is just top-notch, the best in the business right now. This chart kind of puts GANs on the family tree. See, a lot of other models try to learn what's called an explicit density. That's a fancy way of saying they try to figure out the exact mathematical formula that describes the data. It's like trying to write down the perfect, precise recipe for a cake. GANs? They do something different. They're an implicit model. They never bother trying to write down the recipe. They just get really, really, really good at baking cakes. And that direct, hands-on approach is a huge reason why they're so powerful. So that brings us to the end. The progress here has been absolutely mind-blowing, which leaves us with a pretty profound question to think about. As this technology keeps getting better and better, what happens when we truly can't tell the difference anymore? What does it all mean for our world when that line between what's real and what's generated completely disappears?